Hi, in this video I'm going to talk about Axiom of Completeness and Archimedean Property. First of all, I will talk about the Axiom of Completeness of R. Let S be a non-empty subset of R. If S is bounded above, then the supremum must exist. Well, first of all, what is an axiom? Well, an axiom is something that cannot be proved, and it is just proposed by mathematicians. It is just like the ground, and without the ground we cannot build anything, because there is nothing we can build on. And therefore, we have to propose the axiom of completeness, which is very important. And from the axiom of completeness, we can derive that if S is bounded below, then the infimum must exist. And I will leave it as an exercise. And the second, I will propose the Archimedean property. Let x be a real number. There exists some n which is a natural number such that x is smaller than or equal to n. Well, if x is a negative number, this is rather very obvious. However, if x is a very large real number, we are uncertain about this. But indeed, from Archimedean property, we see that it is a true statement, and we are going to prove it using the axiom of completeness. So we suppose that there is a real number x such that for all natural number n, x is bigger than the all natural number. The set of natural number is bounded above, and yet as 1 is inside n, then n is non-empty. By the axiom of completeness, we know that the supremum of the set of natural number exists, and let L equal to the supremum of the natural number. So, by the formulation of the supremum for all epsilon greater than 0, there exists an n0 which is a natural number such that L minus epsilon is smaller than n0. Well, in particular, we can take epsilon equal to 1. Then L minus 1 should be smaller than n0. Thus, we get that L should be smaller than n0 plus 1. Well, notice that L is the supremum of the set of natural number, and it is the upper bound on the set of natural number. So, L is bigger than or equal to n for all natural number n. And in particular, if n0 is inside the set of natural number, then n0 plus 1 should be also inside the set of natural number by the definition of the set of natural number. So, if it is a natural number, then L is a supremum and will be bigger than or equal to n0 plus 1. And if we have proved that n0 plus 1 is bigger than L. And therefore, from this inequality, we can see that n0 plus 1 should be smaller than n0 plus 1. But this is indeed a contradiction. And that means for all x inside the set of real numbers, there exists an n which is a natural number such that x is smaller than or equal to n. And we can prove that the infimum of the set of 1 over n for n, which is a natural number, is indeed 0. It is because, first, we know that 1 over n should be bigger than 0 for all n which is a natural number. So, we can obviously see that 0 is a lower bound. And take epsilon greater than 0. In particular, 1 over epsilon should be greater than 0 as well. And by the Archimedean property, there exists an n which is a natural number such that 1 over epsilon is smaller than n. So 1 over n should be smaller than epsilon by multiplying the epsilon to the right hand side, and then we divide the big N to the left hand side. And recall that to prove that it is a infimum, we need to prove that for all epsilon greater than 0, there exists an x0 inside S such that x0 is smaller than epsilon plus 0, because now the 0 is the infimum that we are going to prove. And notice that 1 over back n should be inside the set of 1 over n for n, which is the natural number. And we write that x0 is equal to 1 over back n. And we have that x0 is smaller than epsilon plus 0. And x0 is inside the set of 1 over n for n, which is a natural number. Thus, we get that 0 is the infimum. And we have another proposition. We let that x is a real number and x is greater than 0. Then there exists an n0 which is a natural number such that x0 is in between n0 minus 1 and n0. And how can we prove so? Well, we fix an n0 which is greater than 0, and we put the S to be the set of natural numbers such that it is bigger than x0. By the Archimedean property, S is non-empty, because from the Archimedean property, we know that there indeed at least one m such that m is greater than x0. And also, as we have restricted m to be a natural number, S immediately is a subset of n. And we put n0 to be the minimum of S, which exists because of the well-ordering principle, which states that any non-empty subset of n has a minimum. And by the definition of minimum, at least it is lying inside S. And by the definition of S, x0 is smaller than n0. And since n0 is a minimum of S, n0 minus 1 is not lying inside S. And remember the definition of S, that it is a natural number such that it is bigger than x0. If x0 minus 1 is not lying inside S, it is just violating this statement, and it means that x0 is bigger than n0 minus 1. So we get that x0 is smaller than n0 and x0 is bigger than or equal to n0 minus 1, which means that it is equal to n0 bigger than x0 bigger than or equal to n0 minus 1. And we are done with the proof of the proposition. And this is the end of the video about the axiom of completeness and the Archimedean property. And I will see you in the next video.